Hello everyone, welcome back to my channel. My name is Dr. Yogita Bisht and today we are starting with a new video series called Chemical Bonding. In this particular video series, I will try to cover all the different approaches which contribute to the better understanding of the chemical bonding, which is the modern understanding, like how different atoms or molecule they combine together and why they combine in a particular manner, why do they have a different shapes. So there are different approaches for that. For example, the very basic is the Lewis structure, the Lewis approach. Then we also have the Vesper theory, that is valence shell electron pair repulsion theory. Then we have the valence bond theory and the molecular orbital theory. So there are different theories proposed by different scientists which come with the as we progress through the with the better understanding of the molecule and the structure. So in today's video we will start with the Lewis approach, and here we would like to give credit to another scientist, that's a German scientist, Kössel. He also worked on the same idea. So combined with the Lewis idea and his idea, a new approach was came into picture. So in today's video we will cover that, and in subsequent few videos I will cover the different the aspects of the Lewis approach, because that is the most important one. And like in lower classes also we have already studied about the Lewis structure, the octet rules and all those things, so it will be a kind of recap also. Okay, so but before that, to understand this all approach, it is very important to understand the basic electronic configuration of different atoms. Okay, so if you don't know that, you can do a short recap of that. I have already created a video series for the same. I will provide the link for that, and you can just go through it. All right, so let's just start with this Kössel-Lewis approach. Okay, so before we move to the Kössel approach, I will give a rough idea about the Lewis approach and its structure. So basically what happened is both Kössel and Lewis, they gave their ideas in year 1916. They both worked independently, but they gave somewhat the same result, like the same idea how the molecules are combining, why they are combining. So that is why this approach combined as in whole is considered as a Kössel-Lewis approach. So first we will try to understand the Lewis idea. So what Lewis considered is, he said that at any atom, it can be represented as a kernel. This is a kernel. Okay, and it consists of nucleus and inner shell electron. Okay, so this is the kernel, and he assumed, I'm drawing it here, this is a kernel, and he consider that there is a cube around it. Okay, you can draw a cube. So basically this is a kernel which is nucleus plus inner shell electron. Okay, and he considered that the outer shell electron occupy these corners. There are 8 corners. So he said, depending upon how many electrons are there in the outer shell, they will occupy these corners. For example, in case of sodium, it has the 11 electron available. So its configuration is 1s2, 2s2, 2p6 and 3s1. Okay, so these electrons we can also represent it as neon 3s1. Okay, so this neon, so these 10 number of electrons, he consider it is considered as the inner shell electron. So this is a part of the kernel. So the only electron left is 1 electron. So he said that in kernel, that is in the center, it will have the nucleus as well as these 10 electron, and this extra electron, that is the electron within the outer shell, it will occupy one of the corner of the cube. Okay, Similarly, if we talk about chlorine, for example, or maybe, yeah, so in case of chlorine, we know that the configuration for the chlorine is neon 3s2 3p5. Okay, so these 7 electrons will be occupied. This is the valence shell electron and the outer shell electrons are 7. So they will be occupied at the corners. Okay, so this was the idea of the Lewis, and he said that any atom, it tried to achieve a configuration where all these corners are full. Okay, that is, they try to achieve a stable octet, outer octet, either by losing the electron or by gaining the electron. Okay, so for the sodium, it is beneficial to lose one electron to get a stable octet, whereas in case of chlorine, it is beneficial to gain one electron to get a stable octet. Okay, so this was the Lewis understanding of the valence electron. So he said that he took into care only the valence electron, they are the participating electron, and he formed his theory around it only. Okay, and it keep on talking about the octet, the 8 electron. That is why his idea was also considered as the octet rule. Okay, so first we will try to understand the symbol, and I'll come back to the definition of the octet rule also. So we have something called Lewis symbol. Okay, so what does this Lewis symbol represent? Lewis symbol only show the valence electron. Okay, so I'll give you the example, and there are some exception also, so don't get confused. We will talk about the exception of the Lewis approach also. So let's say we are starting with lithium. Okay, so we know that the available electron for lithium is 3. So its configuration is 1s2 2s1. Okay, so how to show the Lewis symbol for lithium? We are going to show only the outermost electron. So outermost electron is this one, 2s1. Okay, so how we are going to show the Lewis symbol for lithium? We will check how many outermost electron or the valence electrons are there in lithium. So it is only 1. So what we are going to do? We are going to show it, this electron, with a dot. Okay, after lithium we will have beryllium, which has 4 electron. So in the outermost shell it has 2 electron. Okay, so how we are going to show these 2 electron? Like this, with 2 dots. Okay, similarly we have boron, so it will be represented as 1s2 2s3, sorry, 1s2 2s2 and 2p1. Okay, so it has 3 electron in its outermost shell. Okay, so how we are going to show this? Boron 1 2 and 3 electron. Similarly for carbon we have 6 electrons, so configuration is 1s2 2s2 2p2. So total number of electrons are 4. So that is why we represent carbon like this. Okay, and the representation of carbon is very important for obvious reason, because most of the structure or the entire organic chemistry is based on this, like how it bond with the other molecules. So its representation is more important. Then after carbon we have nitrogen, that is 7 electron, 1s2 2s2 and 2p3. So it has 5 electron in the valence shell, right? So that is why we need to show 5 electrons. So how we are going to show that? 1 2 3 4, right? And then we will start the pairing. Similarly, now after nitrogen we have oxygen, so it will be represented as 1s2, 2s2, 2p4. So this is 1, 2, 3, 4, then 5 and then 6. Please make sure that you represent these dot like this only. And then finally we have fluorine and the neon. So fluorine will have 9, 1s2, 2s2, 2p5, that means 7 electrons. So it will be, just a second, 1, 2, 3, 4, then 5, 6, 7. And lastly we have neon with 10 electrons, 1s2, 2s2, 2p6. So it will be 1, 2, 3, 4, 5, 6, 7, 8. So this is how we show the Lewis structure for all the atoms. So similarly you can show it for the next one as well, as I have already shown for the sodium. Let's say for magnesium. Okay, magnesium has 12. So its configuration is 1s2, 2s2, 2p6, 3s2. Okay, so now in case of magnesium, these are the inner shell and this is the valence shell. So I am going to represent only these two electron, not this, the rest of one. Okay, so magnesium can be represented as like this. Okay, so this is the beauty of Lewis structure. We only represent the valence electron, not the we only represent the outer shell electron, not the inner shell electron. Please try to remember this. Okay, now there is a significance also for this Lewis structure, and in the lower classes you have already studied about the group valency. If you can recall that, we have something called group valency. It's not always follow the same trend, but most of the time with the help of this Lewis structure we can also get to know what is the valency of that particular element, that particular atom. Okay, so how do we get to know? Till 1 to 4, if we have the number of electron in the outermost shell from 1 to 4, then that represent the valency of this element. And from 5 to 7, its valency is represented as 8 minus electrons, whatever electrons are there. Okay, so to explain this, for example, lithium, what is the valency of the lithium? So in this case the first rule applies because it has only one electron. So if it has a one electron, its valency is 1. If it has 2 electron, its valency is 2. If it has 3 electron, its valency is 3. If it has 4 electron, its valency is 4. So here the first rule applies. But afterwards, if you have electron, outermost electron 5, 6, 7, in that case its valency will be 8 minus whatever the electrons are there in the outermost shell. So in this particular case we have 5 electrons, right? So its valency will be 8 minus 5, that is 3. Okay, similarly in case of oxygen it has 6 electrons, so its valency will be 8 minus 6, 2. In case of fluorine it has 7 electrons, so it will be 8 minus 7 is equals to 1. Okay, so most of the time this rule applies. In more complex cases, certain elements they shows more than one valency, so it is a very simplest form of representing the valency. But yes, it do come from the Lewis approach. That is why we need to give the credit, and it do give us the basic idea. Okay, so I hope everything is clear till now. So we can also quickly move to the octet rule, and then I'll give you the idea about the Kössel's contribution, because this is Kössel-Lewis approach, right? So first we will talk about the octet rule. Okay, So octet rule, as I already mentioned, any element, it just, according to Lewis, it just try to either lose electron or gain electron or try to share electron somehow to complete its octet. Okay, and this is what the octet rule is all about. Okay, so according to this rule, I'm writing the definition. Atoms can combine either by transfer of valence electron from one atom to another, that is either by gaining electron or losing electron, or by sharing of the valence electron. We are again and again talking about the valence electron. Why? Because it do not consider the inner electron, it only talk about the valence electron. Okay, in order to have an octet in their valence shell. So this is what the octet rule all about. So this rule means somehow the atom will try to lose its electron, gain its electron, or share its electron with other atom or other element to somehow complete its octet of the valence shell. Once it completes, then it will not talk about that valence shell again. Okay. So with this, now we are moving to the next approach, that is the Kössel approach. What was his contribution? So Kössel also talk about more or less the same thing. The idea was same as that of the Lewis. He just make it more clear with the help of the words and with the help of the example. What does it says? I'm not going to write the entire postulates. You can read it later on. But what it says is like any element, or for example, it gave the example of NaCl. Okay. So in case of Na, he says that this any alkali metal, for example, it has a tendency to lose electron to form a cation. Similarly, an halogen, it has the tendency to gain electron to form a anion. Okay. So in that case, what will happen? The sodium is going to lose one electron to form cation, that is Na positive, and chlorine will try to gain one electron to form an anion. Okay. And then what will happen, since this has a positive charge, this has a negative charge, they will stay together because of the electrostatic force of attraction. So they will combine together to form NaCl, and this particular bond he consider as electrovalent bond. So from this, the term electrovalent bond come into picture, and they stayed together because of the electrostatic force of attraction because of the opposite charge. Okay, so this was the whole Kössel approach. Let's just try to understand this in a more detail. Okay, so try to recall the configuration of sodium. We know that sodium has 11 electrons, right? So its configuration is neon, which has 10 electron, and 3s1. So what it is going to do is, it is going to lose one electron to complete its octet. Now it doesn't have any electrons, so its configuration is just neon, plus it is losing one electron, right? In case of chlorine, its configuration is neon, 3s2 and 3p5. It has 17 electron. So what it is going to do is, it is going to gain one electron to form anion. Okay, and now the configuration is neon, 3s2, 3p6, which is also considered as argon. Why? Because after gaining one electron, it resembles same as that of the another noble gas, argon, right? So here we have cation and we have anion. So they are going to combine together. It has lost one electron, it has gained one electron to form NaCl. And they are staying together. Why? Because they have the electrostatic force of attraction, and they form a bond called electrovalent bond. And mind you, we have not talked about the covalent bond yet. Here till now we have only talked about, given the example where one has lost one electron, another has gained one electron, and they form the bond. And this concept was given by Kössel. Okay, and then another approach came into picture, that no, it's not only just by losing or gaining the electron, the sharing of the electron is also possible, and that gave rise to the covalent bond. But that approach was given by Langmuir. Okay, so in the next class we will talk about that approach. Okay, so I hope everything was easy to understand, right? Starting from the basic idea of the Lewis, like what he imagined, how he imagined the atom while giving the symbol. Okay, and then we talk about the different symbols and their valency, and finally we talk about the octet rule, like somehow they try to achieve the octet for the better stability. And then we talk about the Kössel's approach, though you already had the idea this actually what happened, but the basic idea was given by the Kössel in the same year. All right, so I'm ending this video here, and in the next video I will talk about the Langmuir's approach for the covalent bond. Okay, thank you.